This video is about salts. You should already be able to identify acid and basic salts and calculate their pH of given ion concentrations like negative log and things like that. Today you're going to be able to calculate the pH of a salt. So salt hydrolysis is something that comes up in some of the AP questions, that when the equivalence point is reached at the titration, the moles of acid equals the moles of base, but there can be three different scenarios. Best case scenario, the strong acid and the strong base has hit an equivalence point of 7, the salt that you made was neutral. And so you just like the pH of 7 and you're done. But you can have a weak acid strong base condition in which the equivalence point will be higher than 7. We're going to actually calculate how much higher than 7 it is based on the salt that you made that was basic. And the other condition where you have a stronger acid than a base, so the pH will be lower than 7 because the salt that formed was acidic, and we're going to calculate just how much lower it goes. If a basic or acidic salt is formed, you have to icebox the salt as if it were a weaker acid or base. It is a weak acid or a weak base. It's even weaker than our normal ones. So what salt hydrolysis means is that the weak part of that salt is going to go through a reaction with water. So the reason the salts can create acidic or basic solutions is because that weaker ion is reacting with the water to form hydrogens and hydroxides. Let's remember that the pH is determined by how many hydrogen ions you have. And let's track those pHs by tracking the hydrogen ions or hydroxide ions in each salt combination. Because not really that you have HCl, it's that you have H's that came off the Cl. Or HC2H3O2. It's that you have H's that left that C2H3O2, right? And so we're tracking those. So in a strong acid, strong base, you create neutral salts. A molecular equation would show that HCl reacts with sodium hydroxide to make salt and water. But what really happens is that the HCl separates because it's strong, the sodium chloride separates because it's strong, and the salt separates because sodium is a soluble group 1 ion. Then the spectator ions, sodium and chlorine, can cancel, and a net ionic equation for any strong acid, strong base combination will just be the combination of hydrogen ions and hydroxide ions to form water. Because there's an equal amount of H's and OH's, that is why the pH is 7, right? But now let's talk about the other harder ones. There's no salt to hydrolyze, by the way. The strong acid, strong base make neutral salts. Now we did that one, I had to fix it. So strong acid and weak base make acidic salts. So the way that works is you'll be given a molecular equation like HCl with NH3, and you'll double replace. The NH3 will gain the hydrogen back from the HCl because it's like more like Bronsted-Lowry theory, and the chloride will be alone. So this is HCl's conjugate to chloride, and NH3 conjugates to NH4+, and there is water present because it says aqueous, right? So it's a salt and water combination. It's really just that the H's are moving though. So in the ionic equation, you'll have H ions separate from the chloride because it's a strong acid, but the NH3 will not separate because it's a weak base. And again, the NH4 and Cl will stay separated because it's, ammonia is a commonly known soluble substance no matter what it's with, and then water just stays. So this net ionic equation shows that the hydrogen's ions can't cancel with anything, but the chlorides can. And the NH3 can't cancel with anything because there's no NH3 on the other side, it's NH4. So its net ionic equation looks something like this. Again, the H2O part is not necessary. I'm just showing that it kind of looks like the salt and water case. So now that you know that, what we're saying is this weak particle that you have in the solution, that NH4 particle, chloride doesn't matter, it was spectating, that particle reacts with the water. So we're going to take that NH4+, react with water, and that means that NH4 is going to give away its hydrogen back. It'd prefer to be NH3 than NH4. And then the hydrogen that was left over will be written as H+, or you can think of it as H3O+ if that bothers you. Another way of writing this, if you want to consider it this way, is write that water as H plus OH minus. That way you can see, okay, NH4+ will attract OH minus, and then that will make the H2O come off, and then the H plus part will be left over. So if you want to write it either way, it's fine. So this is called a hydrolysis equation, and the reason why it's making an acidic salt is actually it's making H ions. Let's do that with a basic condition. So if you have a weak acid and a strong base, you're going to make basic salts. The reason is, here's an example, HF is a weak acid, NaOH is a strong base, and when they double replace, you get sodium with, that should be chloride. So let me just fix it to fluoride, there we go. So sodium fluoride and water. And when you look at this, the strong base ionizes and the salt ionizes because sodium is strong, soluble substance. The sodiums, because they're soluble, are always spectators and they'll cancel. And so our net ionic is just the HF that had nothing to cancel with, the hydroxide, the fluoride, and the water. Again, water is optional, like it should be there present the whole time. but for balancing purposes, it's kind of nice to have there. So what we're saying is this fluoride who's floating around, it feels kind of naked, right? It's very weak and it can't stay like that. So what it does, it re-reacts with water. So the hydrolysis equation would be that fluoride re-reacts with water and steals back its hydrogen to reclothe it in a way. And the hydroxide come off. Another way of thinking of it is, like I said before, think of water as H plus and OH minus. It might be easier to say, okay, the fluoride that's negative can't go with hydroxide because that's negative. And it has to go with the hydrogen ion to make HF, and that means hydroxide's left over. So the reason why we say it's a basic salt is actually because the salt part re-reacts and forms hydroxide ions, which would affect the pH. So here's how we'll calculate it. It says calculate the pH when 25 milliliters of 0.1 molar hydrochloric acid is titrated with an additional 25 milliliters of 0.1 molar base. You might already be able to see that both of these come out to be 0.0025 moles by multiplying the molarity by the volume, and that means we're at equivalence. There's no acid or base left over because 0.0025 moles of strong acid and 0.0025 moles of strong base were used, and that means you made 0.0025 moles of a salt in a 0.05 liter solution, 25 acids, 25 bases, but that salt is neutral. So you're done with the calculation. You're just like, neutral salt, pH is 7. Best case scenario. Let's work out two of the worst case scenarios, right? So strong acid, weak base. So calculate the pH when you have the same titration, but I changed the base to NH3 and I gave you the how weak the base was to remind you that it's a weak base. So again, the same calculation we had before, where we multiplied the molarity times the volume and found out how many moles we had, and we realized again that there's no acid or base left over because the 0.025 moles of salt were formed in the 0.05 liters of solution. That came from the 25 milliliters, and the 25 milliliters changed to liters. So now that you have this salt is not neutral because you had a strong acid. So we have to icebox this as if it was a weak acid, right? Because it's an acidic salt. So what we would do is say each ion is unknown, so there's x squared, over the molarity. Remember, that's why I keep telling you that how many moles we had. It was 0.025 acids and bases, so that means you also make 0.025 salts, but that's moles. So I divided by the liters of the total solution so that we have a molarity. Another key problem is that they gave us how weak the base was, but what kind of salt is this again? It's an acidic salt. So if it's an acidic salt, I should be using a Ka. So we have to change the Kb to a Ka by dividing from a Kw. On your reference table, it says that Ka times Kb is Kw, similar like H times OH is Kw as well. So we have to just fix the K because they gave it for the weak base. We wanted it for the salt that it forms. A weak base forms an acidic salt. So we're kind of conjugating the substance and conjugating the K value. Now you can either solve this and cross multiply or cross multiply then solve. I couldn't care less. And then solve for x by square rooting. The x came out to be 5.27 times 10 to the minus 6. That tells you how many hydrogens and conjugates you have. So if you want to know what your power of hydrogen is, you negative log that value and you get 5.27. So this is an acidic salt because its pH was lower than 7. We're going to do a similar calculation, but for a basic salt. So this time I gave you the exact same numbers, but I changed it to acetic acid, and I told you how weak that acid was, titrating with a strong base. So again, no acid or base left over, but because you use 0.025 moles of acid and 0.0025 moles of base, you'll then form 0.0025 moles of salt because 1:1:1 ratio. And if you add 25 milliliters to both, you'll get 50 milliliters, which is 0.05 liters of solution. We need to know that because ice boxes only get molarities, right? So this looks up really similar. X squared over the molarity is a K, but remember the K is for a basic salt, and they give you how weak the acid was. The acid is going to turn into a basic conjugate, a basic salt, and so we need to conjugate our K. Since they gave us a Ka, we need to change it to a Kb. This is really common, so just be aware that that's probably going to happen in salt conditions. So we just divide it from the Kw, cross multiply and square root, and get our x value, which happens to be the same as before, because nothing has really changed. I haven't changed any of the numbers. I only changed which one was weak, right, or strong. But because we're expecting a basic thing, what we're really negative logging is the hydroxide. So we're going to find a negative log of that condition because it's basic, it's the hydroxide ions. So what do you do last if you have a basic solution? Subtract from 14. That way you actually do have a basic value for pH, 8.73. So at this point, you should be able to calculate the pH of a salt.